Okay. So yeah. So this is the second part of the causal inference. And most of the materials are actually come from the Professor Davidian in North Carolina State University. So Professor Davidian is actually a wife of the Chiatis, the author of the book. So they are couple statisticians, very famous statisticians at North Carolina State University. Anyway, so observational studies. So previously in part one, I mainly covered the experiment, right? Randomized experiment. So, that's more related to survey sampling in some sense because you know the selection probability, right? You randomize. So the designer choose which one to, whether this guy belong. So this particular unit is in treatment group or control group. Is under control, right? Under the control. But observational studies is a totally different story, right? We don't really know what is the real cause for the particular choice. So that is the complication, right? Individuals. Sorry. So complication is the individuals choose for some reason, but that's not really clear to us. So individuals may receive treatment, choose a particular treatment according to the someone's expert advice or just own choice, right? So for example, job training, right? So we know that job training can maybe related to causal effect to the employment, right? Better employment. But maybe those who are already active, right? If you are quite active, you search for job training. And so maybe that particular person has a better than, in some sense, than those who choose not to take that kind of a course, right? I mean, job training. So it's not really hard to tell whether the increase of the job training, I mean, the increase of the probability of getting a job is really due to the job training or due to the other factors, right? So that's very it's not really easy problem. So so anyway, individuals who receive treatment 1 may have a systematic difference than those who receive treatment 0. So in the randomized experiment, we assign randomly, right? We purely use the pure random mechanism to determine two groups. So then average other, other characters. So okay, so basically on average, right? On average, the difference between the two groups can be only due to the treatment effect, right? If you are randomized. But if you don't randomize, then the choice can be due to other characteristics. So we cannot really, so that means we may have a systematic difference. So in that case, difference in mean estimator is no longer unbiased. So maybe we want to utilize the auxiliary variable x to control the systematic difference. So that is the basic idea. So the key concept is the confounding factor or confounder. So if a variable is related to both the choice of the action, right? The choice of action and the actual outcome, then it is called a confounder. So there could be several confounders, of course. And then suppose it's a big if. Suppose that confounding factors are known. That means you suppose the choice, right? The choice of the treatment or control is only due to, for example, gender. Suppose. Then within the gender, it's essentially random, right? So that is the basic idea. So the confounding variables are known, then within the same, among the individuals who share the same confounders, all the factors associated with the selection outcomes are taken into account, because you use the same subgroup and compare difference between the control group and treatment group within the same confounding factor. Then that's the magnitude to the treatment effect. So that is the basic idea. So that is, assignment of treatment is effectively at random for individuals sharing the same confounders. So we can formally express it as this. So this is the definition of the confounding factor in some sense. So this confounding factor make Y and A to be independent conditionally. So this is a kind of a classical example. I mean, so one example is A. So we are interested in whether smoking is a causal effect to the lung cancer, right? So we know that it's a causal effect, but in the beginning, all the days, it's not really clear. Especially R.A. Fisher believed that, well, it's an association, not causation, right? I mean, so the data says that, the data clearly says that smoking has a higher rate of the lung cancer patient. So that's true. But Fisher himself is a heavy smoker, and so he declined to the hypothesis that smoking leads to lung cancer. Rather, he said that, well, there may be some unobserved confounding factor that, for example, stress, right? If you are highly stressed, then you may smoke, and also because of the stress, you may get you have a high chance of getting cancer. Okay, and so that is the kind of R.A. Fisher's argument a lot of times, but later with other more rigorous analysis, smoking is in fact causal, has a causal effect to lung cancer, right? So don't smoke. I used to smoke, but not anymore. This is a big assumption. So no unmeasured confounders assumption. So because we don't know, right? We don't know true confounders. So the best thing we can hope for is that the auxiliary variable turns out to be include all the confounders. So that is the big hope, but that is commonly used assumption. Although it doesn't mean that the assumption is true, right? It only means that this is the key assumption that requires the leads to any scientific conclusion. So that is the point. So the auxiliary variable contains individual characteristics recorded in the observed data available to the data analysis. So in general, there is no guarantee that all the confounders are included in X. We assume, right? We assume that the confounders are all included in X, so that we have this assumption, conditional independence. So this is an assumption that we will use, and that assumption is can be called no unmeasured confounder assumption. Okay, so this is also called the ignorability assumption. Okay, so the difficulty is it's just assumption. It's just what we believe. We cannot really test it, right? So it's impossible to verify from the observed data only that whether this assumption is true or not, unless you repeat or you have other expert knowledge to verify that. So we cannot really verify from the data. So here's so under some assumptions, mathematical assumptions, we can get a result. So three assumptions we're gonna employ. The first assumption is the Sutba assumption, right? So that's we already use. So why? So observe. This is the observed run, right? So this is the observed observation, and this is the potential outcomes. And A is the treatment, right? A is a treatment or control indicator. So Sutba plus NUC assumption. So we can call it Nuka, right? Because this A is actually assumption already. So Sutba plus Nuka. And third one is positivity assumption. And PA, right? Pa. And this assumption is that the probability of so it's like if you think about responding probability, this is just a means that this response probability is always positive in the sample support. Okay, in the support. So these three assumptions we need these three assumptions to show equation 2. So equation 2 is the identifying assumption that we can. So this is what you. So right side is what you want to compute, right? This is what you want to estimate, and the left side is what you have as a data, right? This is your data. So A, X, and Y is your data. So you have basically this is what you have, right? Data, and this is what you want, parameter. And so this is basically identifying assumption. So identifying means that an equation, identifying assumption means that it's an equation that leads to estimator. So using this, we can develop an estimator. But this is we want to prove it. Okay. So okay. First, yeah.
So for the part your third assumption, yeah, is it correct to interpret this like any individual included in the data set? I mean, it is possible for them to get that treatment. I mean,
You mean the first condition?
The third condition.
So the one, yeah. So that's a good question. So anyone in the population was sample, right, can be have either so has a positive choice of the one of the two. So you don't have a so one possible if you have a zero probability, right? So that means certain part of the sample you don't have a choice. So that's not really what we want to consider.
So to everyone we can assign treatment in a hypothetical.
So hypothetically, everyone have a freedom. Choose one of the two. Something like that. Okay. So proof itself is not really difficult. Just use the assumptions very carefully. So the first assumption, suitable assumption, we have a y1a times y0 1 minus a, right? So that is the definition of the suitable. And then because a given a equal a, small a, that means you just take the one of the right, only one. So that means you basically if a equal to 1, so a is 1, then you will choose this one. If a is 0, you will choose this one, right? So that means this is this one. Okay. And then, okay, so that is a sutuba. And second assumption is the nuka. So ignorable assumption means that this guy, right? This guy becomes this, right? This is exactly this one. And then the potential outcome Y. So potential outcome YA is independent, conditionally independent of the action, right? Given X. So that is this assumption. Okay. And then if you compare these two, so if you compare 2 and 3, we seems to be already proving, right? This one. So we proved this one is equal to this. This one is equal to this. So that is this one is equal to this, right? We proved this. And this guy is basically taking the expectation of both sides, right? So taking the expectation of both sides means in the major theoretic point of view, there's some additional step. So that means, so this is actually equal almost everywhere, right? So with the property measure 1. So that means we want, so that means if you take the expectation of this, then we are taking the average of the on the marginal distribution of X, and then this guy is a expectation of the marginal distribution of the X at A, right? X and A. So that means we want this to be, we know the inside expectation are equal almost everywhere. So then that means because the almost everywhere equality already means that they are in the same space, same support. So that's kind of a major theoretical argument, but that's a kind of technical assumption that you want to guarantee to achieve our goal. Okay. So now, so once we prove this fundamental result, right? So once we prove fundamental result, now remember what we want to compute is the difference on the right side, right? So expectation of Y1 minus expectation of Y0, right? And that is actually expectation of the left side, the difference of the expectation side. So left side inside the expectation is just the conditional expectation. So essentially regression model, right? Y given X and A, which is the regression model. So that is one approach. So basically, the equation 2 implies the tau it can be written as this. Right? So originally tau, the definition of tau is an expectation of Y1 minus expectation of Y0. So that is the definition. But the property fundamental result 2 is that this guy, first guy is equal to first guy, right? Second guy is equal to second. Okay, so that is basically, oops. And then this one is equal to this. And this guy is equal to this. Okay. So we have only to compute the conditional expectation inside the outer expectation. So then we only have to compute this function. So this is sometimes called the Q function. Okay. So because it's a function of X and A, right? Q function. So computing this Q function is sometimes called Q learning in machine learning area. pure learning. So the dynamic treatment rhythm that I plan to cover next class has a close connection with the reinforcement learning in machine learning literature. I mean AI. So naturally we may move on to reinforcement learning if I have time. So everything is connected. Start with the sampling and missing data and causal inference and dynamic treatment rhythm, and then eventually reinforcement learning. So it's like a evolution, right? I mean, essentially.
So what is the main connection with dynamic treatment design and causal?
I'm sorry?
What is the main connection with dynamic treatment design and causal?
I don't know.
What is the missing data for the dynamic treatment design with the missing data?
Right.
What is the relation?
Relation between I mean this one?
Yeah.
Well, so causal inference here, I only cover estimation of a tau, treatment effect, right? But later, in the dynamic treatment, we are actually determining a best action. Okay, so it's two things: parameter estimation part and action part. So that is adaptive way of learning. So dynamic, because so the action means you collect the data, right? So you collect data, then you have more information. So then you can update your parameter. And then once you have an updated parameter, you can have a better position to determine A. Because you have so it's like a EM algorithm in some sense. I mean, it's not really EM, but you have basically your action chooses the next, which one to choose, right? Which one to collect. That's exactly reinforcement learning.
But here you are talking about observational study. So treatments are assigned without any control of the investigator.
Right.
So here are you? I mean, will there?
So right, reinforcement learning, we are control. Right. We are doing optimal decision. Okay. Oops. What's going on? Okay. So now the problem is how to compute the Q function, right? So we are statisticians, so we use a statistical model, right? So it's not difficult because we basically it's a regression. Y on X and A, and you observe Y, you observe X, you observe A, no problem, right? It's just a regression. So that is basically what's going on here. I mean, you can build if you are more technical person, then you can build an parametric regression here, right? But for now we just use parametric model and build the parametric, estimation. And then how to compute beta hat? You can use the linear regression to obtain beta hat. Okay, so then we can obtain beta hat here, and so that we can compute estimator of tau. So that is the outcome regression model approach of the causal inference. I mean the average treatment effect estimation. So you can now see that this is exactly imputation approach in the missing data, nothing else. It's really it's an imputation approach, and then once how to compute the variance of this kind of problem, we already know, right? We can use linearization. So yeah, I mean that's we studied this already. So in some sense, missing data is actually more fundamental than causal inference, because we already know how to deal with this in the class during this semester. So it really transported to nice application of the missing data causal inference. But you know, a lot of papers in causal inference these days. So you know, because it's newer. So survey sampling is more difficult to publish, mainly because it's old, right? You have a long history, then it's very hard in 1950s and 60s. If you look at the JASA in 1950s and 60s, a lot of sampling papers at the time. But it's not really new anymore, right? And so then missing data take over, and it's very hard. 90s, I mean, 2019, 2000, 2000, maybe 2010, a little bit. But now it's more moving toward the causal inference and dynamic treatment regime and so all these things. But the fundamental concept are pretty much similar, but application and context are different. So nothing new under the sun, some sense. Okay. Now we can actually, so this is one way, right? This is one way. And now we're going to introduce another approach that we already know in missing data class. So that is propensity score approach. So the idea is, because we have this, right? This is an indicator function. It's like delta. So we can apply propensity score function and develop the another estimator. So the propensity, so it's essentially probability, right? I mean, probability for choosing a equal to 1 given the covariate x. So then inverse probability propensity score weighting is basically utilizing the pi x function directly. So how to do that? Well, the definition of right, and so we use, this is pretty much Horvitz-Thompson estimation. So if you okay, so let's do it one by one. So in the outcome, in the propensity score approach, x and y are treated as a fixed, and only a is treated as random. So we are doing some kind of mu hat given x and y 1 conditional on so okay. By the way, I should write it as a, so you can write it as a 1, right? By Stuba. So by Stuba, we can write this way. And then once you write this way, this guy is no longer depends on AI, right? Because previously you have yi is a function of AI and 1 minus AI, so it's kind of complicated, right? So if you do it this way, you can actually evaluate the expectation more easily, so that you basically compute the So here you essentially assume the positivity assumption. Because if this is not positive, then you cannot really have a cancellation, right? 0, 0, right? Situation. So positive assumption and yeah.
So if positivity is not satisfied, then the estimator itself is not.
It's not really comfortable, right? Right. So that means you cannot really
Consider this case.
you cannot really construct it. I mean, estimation is impossible, right? Essentially. So here you actually has a Nuka, I had to say. Because well, actually this, because what does here we are basically assuming that a given ai given x and y1, right, is equal to ai given x, and that is pi x. So that's basically what's going on here. So we use 3 assumptions, right? Okay. So, and then similarly, we can estimate what mu 0, right? Same thing. It's just a different probability, different event, 1 minus a event. So a equal 0 event. So we have the same. So the unbiased requires the same 3 assumptions in addition to pi x is known. Okay. So then pi x is known, then this is our estimator of tau. But in practice, so pi x is known if we are, it's an experiment. If it's an experiment, we know. But in the observational studies, we don't know. So we need to make a statistical assumption and build a model and then estimate it, like a logistic regression or something. So gamma is the parameter in this case. Then this is pretty much the same, same estimator that we studied in chapter 7, right? Propensity score method. So the theory directly follows, and we know all how to compute the variance estimator, all this. Okay. So that's basically propensity score approach, and then naturally we want to combine 2 models, right? 2 models to develop the doubly robust estimation. So outcome. So okay. So both requires suitable NUC and positivity assumption. And so outcome regression estimator requires a model assumptions on Y regression model, outcome model, and IPW estimator requires a model assumption on the propensity model. Okay, so selection probability model. So this is actually model assumption. It's not really known. I mean, we make a model. So there's a risk, right? I mean, potential risk for model misspecification. So we want to reduce the risk. So one way is to use doubly robust estimation. So that's one possible approach. So this is the basically doubly robust estimator. Okay. So we have two models, right? So and then estimated so pi and q function. So this is the form of the, so looks familiar, right? You have a regression predictor and residual, and then weight, right? It's pretty much the same. And mu zero, we have a predictor for mu, right? Predictor for a equals 0, and then residual, and then the weight should be the event in this case is a equals 0 event. So then so the only difference between the missing data and causal inference is that the mu one part is essentially the same, but the mu zero part we reverse, right? A 1 minus a as a delta, some sense, and then apply the same W robust estimate. Okay, so that is the basic concept. I mean, you can so how, so when you, if you remember, how did we really compute the show the W robust? Well, key idea is you can consider an estimator without missing data. Okay, this is your estimator you would observe without missing data, right? And then basically you take the difference. Okay, so if you take the difference, then what you get is essentially okay. Basically, well, let's do it one by one. Q xi 1 beta hat plus ai minus pi xi gamma hat y. So y, you can write it y1i here because you have a multiplication ai, right? So this term 1 minus ai doesn't show up, right? So you will have just this way, and then basically you have a minus q1 q hat essentially. Okay, minus, right? Minus 1 over n I equal to 1 to n yi 1. So basically we have some nice form, which is the I guess ai minus pi xi gamma hat minus 1 times yi 1 minus q hat 1 xi 1, something like that. So basically zero expectation on the PS model, and this is zero expectation, right? Expectation, zero expectation, zero on the outcome regression model. So that if one of the two models is correct, then expectation will be 0, right? Y0 is the same thing, only difference is that you change. A will be changed to 1 minus A, and denominator will be 1 minus pi. Okay.
If that's the doubly robust, because either one of the model is either PS or your model is correct, so then we are getting that.
So either outcome regression model is correct or the purpose model is.
So in that sense, it is doubly robust.
Hmm?
In that sense, it is.
In that sense, it is totally robust. So it is doubly robust. And turns out that it is locally optimal. So locally optimal means that under the model, when both models are correct, then this guy. So if you can think of this class, so the idea is so this is basically without this. This is just the propensity score estimator, right? So this is propensity score estimator, and this guy is what? Estimator of 0. Okay, estimator of 0, and then find the optimal H using the technique. So that's not really easy, because if we know the form, okay, so again, if we know the form, for example, if I know that this is a linear form, something like this, then the unknown, so unknown noise parameter is a finite dimensional, right? And then you can compute the variance, asymptotic variance, in terms of beta, and solve for it, right? Optimize it a little bit quadratic function, so you can find the optimal beta hat. But this is function, right? So that means this is not really parametric class. So this is a kind of a infinite dimensions. So in the book that I will so in the class that I will cover in the book, cerebral theory book, we will rigorously study how to compute the optimal solution. Okay. So that is the most, I think that is kind of research level topic. I mean, if you are interested in publishing papers in top class journals nowadays, this is the kind of knowledge level of the technique that you need to master in order to publish. If you just assume a parametric model, then referee will not be impressed. You are solving easy problem and reject. So we need to do some. I mean, also, this is bigger class, right? I mean, this is a bigger class, and this is a really general class. If you think about that, I mean, right? This covers a lot of, estimators. So maybe this is a reasonably wide class. And then in this wide class, you want to find the best one. So that's basically the topic that we want to study more rigorously. in the next semester. So that's pretty much all I have prepared for today. Any questions?
So these development is already done. So
Huh?
studying the class of functions H over any.
Yeah, this is actually now have a book. You have a whole book for this kind of theory.
How to get optimal function of H?
Huh?
How to get optimal H?
Optimal H. So that's actually exactly. So let me. That's a good question. Let me. Actually, this is not really new. We already studied this. So where we studied this, I can show you. Yeah. So remember. Yeah, believe it or not, we covered it. Yeah, this one. So I should maybe I should share. Okay. So basically this is I mean, so this is basically y minus zeta, right? Y minus zeta. And then basically we generalize. So without this, right? Without this is just the propensity score, right? Propensity score is meter. And we basically play the same trick. So basically in our notation, this is hx essentially. And we want to find the optimal hx. And that is originally proved by James Robbins. So actually I gave a proof. So idea is we cannot really. So the technique is we conjecture. Okay, we conjecture what is the best one, which is the B star, and then show that this guy is uncorrelated with it. So yeah, you will be surprised that you already studied, but it's true. we proved it. Huh? Yeah, that is kind of projection. Yeah, right. Right. So because we want this to be orthogonal. And this is actually zero mean so D. What is DB? DB is this guy, right? This guy. So this guy is zero expectation no matter what. Right? Because of this zero expectation. So you're kind of projecting and orthogonalize. But this is heuristic argument, and we want to like to cover it more rigorously. That requires some more theoretical depths. Okay.
Previous slide where you defined the estimating equation. So there basically B theta is a and so. So here basically instead of equation. So instead of specifying B theta xi to a parametric function, by using this estimating equation, you are this is a semi-parametric set of that. That's why so you are interested in
right. This is a function. I mean,
yeah, you are interested in
general function.
B theta xi that satisfies this.
Right.
So that's why we made this semi-parametric.
So this is the only restriction is that Px is just the function. Px is integrable. I mean, general function of x. So that the expectation. So if you take the expectation delta and pi, and this guy will cancels, right? So then this guy will be just any mean zero. Mean zero is meter, right? So if you know this is x beta something, then you can construct the optimal estimator relatively easily. But this is more difficult because this is function. I mean, infinite dimensional, becomes a space, function space. Okay.